Thank you everyone for attending this talk. Today I will be telling you about a private, secure, and practical algorithm for multi-party reach and frequency. This is Joy work with Badih, Ben, Ravi, Jiayu, Evgeny, Yao, and Kreuter. Our work is motivated by applications in the ad domain where there are multiple publishers showing the same or similar ads. Each publisher I manages to reach a set Si of users. And our goal is to first compute the total reach across all publishers, which is simply the number of unique users that is contained in the union of all the SIs. Furthermore, we would like to compute the so-called frequency histogram, where the kth entry of this histogram, which we call k frequency for short, is the fraction of users that are reached k times across all publishers. For convenience, we typically cut off the frequency histogram at some number, like 10 or 15, and then group all the k greater than 10 or k greater than 15 together into a single bucket. The model of privacy that we use will be the so-called multi-helper model, where there will be multiple workers and an aggregator, and they will together run a secure protocol to compute reach and frequency. And our goal is to ensure that every collusion of all but one parties cannot violate the user's privacy. The specific notion of privacy we will use is differential privacy, and we will go through that in more detail in a few slides. But before that, let me mention that as our title suggests, our protocol should be practical and scalable. And this means that we would like to be able to support many users, up to as many as 1 billion users in the reach. We would also like to be able to support many publishers, up to 100. And we would also like to have a small communication overhead in running this secure protocol. Due to time constraint, I will mostly be focusing on the reach today and only touch upon frequency just a little bit. And even before we talk about the multi-helper model, let us start with the simpler and more popular central model of differential privacy. In the central model of differential privacy, there is a trusted aggregator. In this case, the publisher can send their data to the trusted aggregator, who then produce the estimated reach. The notion of differential privacy states that if we take a look at two neighboring datasets, the distribution of the output of the algorithm doesn't change too much, and this is parameterized by two parameters epsilon and delta. In our case, we consider two datasets to be neighboring if they differ by adding or removing a single user across an arbitrary set of publishers. In other words, we are considering user-level differential privacy. In the central model of differential privacy, we only enforce that the final estimated reach be differentially private. Note here that there is no protection against the aggregator at all, and it is entirely possible that the publishers send their raw data to the aggregator. And this is why we need to trust the aggregator in the central model. And this might not be the most suitable for the setting that we are in, for which there might not be a single party that can be fully trusted. Despite this drawback, the central model is nice, that it is easy to design an algorithm for. In fact, for our reach problem, the algorithm is as simple as letting each publisher send their raw data to the aggregator, then let the aggregator compute the true reach, and then add to the true reach some appropriately calibrated noise. This would already give a central DP algorithm for reach. However, as we said earlier, we would like our protocol to be scalable and being able to support many users and many publishers. And having each publisher send their raw data to the aggregator is simply too costly in terms of the communication in our setting. And this brings us to our first tool in our work to reduce the communication complexity of the protocol, and that is sketching. The sketch that we use is a modification of the classic Bloom filter sketch. And just to quickly recall, in Bloom filter there are m registers, each set to 0 initially. And there is a hash function h that hash each user ID to a uniformly random number from 1 to m. When a user arrives, we simply hash their user ID and then set the corresponding register to 1. Bloom filters are easy to merge by simply taking the bitwise OR. Furthermore, the reach can be estimated by looking at the number of non-empty registers. All these are good, except that the accuracy of Bloom filter becomes very poor when the reach is much larger than the sketch size m. And this leads us to our modification of the Bloom filter sketch, which we call the liquid legion sketch. It's almost the same as the Bloom filter, except that instead of having a hash function that map each user ID to uniformly at random register, we take a map such that there is more probability that it gets mapped at the beginning of the sketch than at the end. And this probability decreases geometrically as we go to the right of the sketch. This can be thought of as a smoother version of the so-called ball and pin trick. Our liquid legion sketch is much better at handling a large set size when compared to the sketch size. For example, for the billion user case, we can accurately estimate the set size using only about 100,000 registers. Alright, so how do we use this liquid legion sketch in our protocol? In the trusted aggregator setting, each publisher I can now send their sketch instead of their entire set Si to the trusted aggregator. The aggregator then merge these sketches and then compute the number of non-empty registers in the merged sketch, which, as we discussed earlier, can be used to estimate the reach. This is the entire protocol, except that it's not yet private because the number of non-empty registers depend on the input itself, and this can be a sensitive data. To make this differentially private, we can add to it a discrete Laplace noise, and this would be a differentially private protocol in the trusted aggregator model. Notice here that each publisher communication now scales with the sketch size instead of the set size, and as we discussed earlier, the former can be much smaller than the latter. Alright, so that's the reach estimation algorithm in the trusted aggregator model. As we discussed earlier, we would like to work in a model that requires less trust. Specifically, we use the multi-party DP notion. Here, in addition to the aggregator, there are multiple workers, and the notion of DP here is that we would like a collusion of all but one workers or aggregator to have their view still be differentially private. Furthermore, we relax the notion of DP from a statistical one we used earlier to a computational one. This allows us the use of cryptography as well, which, as we will see in a moment, will be very useful. At a high level, our protocol has three phases: the sketch creation and transmission phase, the reach estimation phase, and the last phase, the frequency estimation. For the purpose of time here, we will only focus on the first two phases. Before we describe the protocol, let us recall that we would like to satisfy now both privacy and security. The latter will be achieved via encryption, and the former via adding noise. However, there will also be complications that arise in our protocol because our protocol will leak some intermediate states that will be sensitive data. And to make this data private, we have to add noise. However, we have to add this noise carefully, as otherwise we might destroy the utility of the protocol. With that in mind, let us start by describing roughly the sketch creation and transmission phase. Recall again that each publisher I can construct their own liquid legion sketch, and they will send these sketches to the worker. Instead of sending them as a bit vector, they will send them as indices of the non-empty registers. This helps reduce the communication further. However, this wouldn't be private because these indices depend on the input. To fix this, we encrypt each register index with the public keys of all the workers and the aggregator. However, even with this, it's still not private because each publisher's number of non-empty registers is still revealed in the clear. To fix this, we then generate a number of noise registers which are sent along with the true registers to the workers. Note here that the noise register will have a special designated register ID, which I denote by C here. As we will see in a moment, this will be important in ensuring that the protocol has good utility. That's roughly the sketch creation and transmission phase. Let's move on to the reach estimation phase. So in reach estimation phase, the workers and aggregator communicate in a cycle, and each party decrypts its own key from the encrypted register, and then it shuffles all the register and then forward it to the next party. Once this is done, we are left with a set of indices, and as stated earlier, the noise register have a special register ID, so we can remove them from this set, which give us the number of non-empty registers, which can then be used to estimate the reach. In the actual protocol, the workers and the aggregator have to add some noise as well to achieve DP, but we will not have time to go over those details today. To conclude, we have given a multi-party differentially private protocol for reach and frequency. Our protocol implementation can be found online on GitHub. There are some related and ongoing work, such as how to do privacy budgeting over multiple queries, or how to answer time-related reach and frequency query. And that's all I have for today. Thank you all very much for your attention. Thank you.